The warm-up says John pulls a wagon with 20 newtons of force at 65-degree angle above the ground. Amy pulls her wagon with 20 newtons at 35-degree angle above the ground. If both wagons have equal mass, which will accelerate more? So in this particular question, we're just looking at how changing the angle of that force will affect the net force on the object and thus affect the acceleration, because we're saying these are equal in mass. So we're really just looking at how the angle affects that net force and thus the acceleration. And if you go back to the math, you can solve it mathematically, but you can probably, hopefully, get an idea just by looking at the picture regarding where more of your force is, because when you do pull something at an angle, you have both forces in the horizontal and vertical directions. Okay, and so if we take a look, let me go ahead and show you how I would solve this. So we take a look at this, and here's the information from the question. So hers is 20 newtons at 35 degrees, his is 20 newtons at 65 degrees. Okay, and you can see right now just by looking at the length of those vectors that hers is going to have a greater amount of force in the horizontal direction. You guys agree with that, just looking at the dimensions of the triangle? But you can solve it mathematically if you want to. So let me go ahead and do that. If I wanted to solve for this horizontal component, and that's the one we're going to care about because that's the one responsible for the acceleration of the wagon. Okay, then I would say that the cosine of 65 degrees equals, and again, cosine is the ka in SOHCAHTOA, so it is adjacent over hypotenuse. The adjacent would be f in the x direction over 20. So you would multiply 20 times cosine 65, and you would get 8.452 newtons. You can do the same thing over here. Cosine 35 equals f in the x direction divided by 20. And again, 20 times cosine 35 gives you 16.383 newtons. So again, looking at the numbers, you can also see it. But you can also just look at the dimensions of those triangles. You can tell this is going to be more horizontal than this one. And again, it is the horizontal force that is going to be responsible for the acceleration of the wagon across the ground. The smaller the angle, the greater the amount of force is in the direction of acceleration. Thus, the force at 35 degrees, that's Amy's wagon, will cause greater acceleration of the wagon in the absence of friction. Okay, so again, if you have more of your angle in the horizontal direction, then more of your force is horizontal, and when that happens, you're going to have greater acceleration because you have more net force in the x direction. She's got almost twice as much, not quite, but almost. All right, so again, make sure that you answer that question in My Open Math so that you get credit for your warm-up today. But again, Amy would have a greater acceleration of her wagon because she has a greater net force in the x direction. Questions about the warm-up? All right, we are going to take some notes today, so if you don't already have out some paper, go ahead and get that out, and then we're going to get right into it. It's going to be more practice like you did yesterday. All right, so again, we're going to do more practice like we did yesterday, but we're going to add a little bit to it. Okay, we're going to a little bit more difficult as we go because you'll need to have practice with all this stuff. This one says, a crate with a mass of 31 kilograms is pulled over the floor with a diagonal force of 275 newtons. The force makes an angle of 24 degrees with the horizontal. Assuming there is 100 newtons of friction between the crate and the floor, find the acceleration of the crate. So we're adding friction in, but I actually took out a couple steps by giving you the force of friction. So I didn't give you the coefficient. That would be a little bit trickier to solve. I have one like that in a minute. We're going to start a little easier and then get a little bit harder as we go. Okay, so looking at this question, let's go ahead and draw the free body diagram. I added the information from the question here that they told us. They gave us the mass of the crate. They gave us the angle at which this 275 Newton force is being applied. Okay, and we need to make a free body diagram over here. So I'm going to find the x component of this force. Remember, the first step, if you have a force at an angle, is to get the components. Okay, so make a triangle and get the x and the y components of that triangle. And to do that, you're going to be using SOHCAHTOA. Okay, in this particular case, to solve for this red vector, my force of tension in the x direction, I need to use cosine because this is adjacent to my angle. And so I would say that the cosine of 24 degrees equals adjacent over hypotenuse, which is ft in the x direction over 275. And then we're going to multiply both sides by 275 to isolate this variable and have 275 times cosine 24, which is about 251 newtons. I'm rounding a bit here because it just saves me a little bit of space on my free body diagram. Okay, it'll be close enough for this example. Now we're going to do the same thing, but for this vector in the y direction. Again, get both components, okay, x and y. Okay, this one we're going to say sine of 24 degrees equals opposite over hypotenuse. This is the SO in SOHCAHTOA. Okay, so ft in the y direction over 275. So again, in your calculator, if you're typing it out, and if you want one, you can grab one from the side in a minute. You type in 275 times sine 24, and that would give you 112 newtons. Again, I'm rounding all these numbers, but that is going to be an upward force. Okay, so again, if you pull something at an angle, part of your pull is going to be horizontal, part of it's going to be vertical. In this particular case, he is pulling both to the right and up, so that's where I'm going to put those vectors on my diagram. But those aren't the only forces acting on this crate. Okay, I also need to include my force of friction, because in the question it gave it to me as 100 newtons. Okay, and I also need to include my force of gravity, okay, Fg. That's the weight of the crate. Now they didn't give me the weight, but they did give me the mass, 31 kilograms. So I can find the weight. Fg is m times g. I have that equation on my board still. We used it in the last unit as well. Okay, and so we're going to multiply the mass, 31 kilograms, times Earth's gravitational field strength, which is 9.8. Okay, again, it's technically negative. I didn't label it that way here, but this is technically negative 304 newtons because it is downward. Okay, but when I draw it on my diagram, I don't have to include that because the direction is shown by the vector. Okay, but there's my 304 newtons downward. Okay, what else do I need to include? I'm still missing something. Anybody know what it is?
Wait. Normal force?
The normal force. Okay, is this crate accelerating vertically?
Yes.
No, he's just pulling it across the ground, right? It's not leaving the ground. He's just dragging it. Okay, so I need vertical forces to be balanced. Right now, I already have one upward force of 112 and one downward force of 304. If I need them to be balanced, I need to add something to the 112 to get 304. I need them to be equal and opposite to each other. Okay, so if you wanted to solve for normal force, it's not going to be equal to force of gravity. It wasn't equal yesterday either. If you have something pulled or pushed at an angle, it won't be. Okay, your normal force will no longer equal your force of gravity because now you have a third force in the vertical direction. Okay, so again, these two together need to add up to equal 304 newtons. Okay, and that means that this needs to be 192. And again, all I did was 304 minus 112 to get that. I'm looking for what I have to add to this to get this. Okay, so 192 plus 112, that's how I get 304. Okay, and now I have balanced forces in the vertical direction. Now, if the question had said that we had vertical acceleration, obviously I wouldn't want them to be balanced. But in this case, the crate is simply being dragged horizontally. There is no vertical motion at all, much less acceleration, so I need them to be balanced in this case. Okay, so I have all the numbers. If you want to label them with the force type as well, you can. Those are kind of over here on this picture. But here is my free body diagram. Okay, you need to be able to get to at least to this point because this is what you're going to have to use in order to solve the questions like this one, which was find the net force acting on the crate so that we can find the acceleration of the crate. Okay, well again, vertically my net force is going to be 0. So the only thing that's going to not be balanced is my horizontal forces. And I can see that looking at it, that I'm going to have a net force in the horizontal direction. But again, as a reminder, your net force must be calculated separately for the vertical and horizontal directions. Vertically it's 0, horizontally, okay, again it's the sum of the forces. That's 251 plus negative 100 or 251 minus 100. Which would be 151 newtons to the right. Okay, so the net force for this scenario is 151 newtons to the right. This vector here is 151 newtons longer than this one. Okay, that net force will be responsible for the acceleration. Okay, so for the last step of this calculation, if we want to find the acceleration, we need to just use F net equals m times a, keeping in mind that this is F net, 151 newtons to the right. Okay, so again, acceleration occurs due to that net force, that total force acting on the object. Okay, F net equals ma, so 151 equals, the mass from the question was 31 times a, divide both sides by 31, 151 divided by 31 is 4.9 meters per second squared, and that acceleration will be in the same direction as the net force, so to the right. Does anyone have a question about any part of this problem? Again, I just added one extra thing. Yesterday we didn't have to worry about subtracting the friction out. Now we do. And sometimes you don't have friction, then it's more like yesterday's problem. But you need to be able to answer these as well. All right, let's try one that's a little bit trickier. Okay, this is about as tricky as they get. It says Tom pulls, and again, if I were you, I'd write this down. Tom pulls a 12 kilogram toy box with a force of 59.5 newtons at an angle of 36 degrees above the ground. The coefficient of friction is 0.27. Find acceleration. Okay, this is as much as I say that. I'm going to give you more tomorrow. But this is mostly as much as you're going to get in terms of the type forces. That's true. This is as much as you're going to get with forces. We're going to bring back in some old stuff tomorrow. Okay, so if I give you something at an angle and I give you a coefficient of friction, there's a lot of steps. I'm just going to warn you right off the bat, there's going to be a lot of steps for a problem that looks like this. So again, if you have a force at an angle, you need to get the components of that force. Okay, I didn't even show the work on this, but I have an angle of 36 degrees. I have the hypotenuse. For this one, I would use sine. And so I would say that sine of 36 degrees equals this y value, my ft in the y direction, over 59.5. Okay, so you would be doing 59.5 times sine 36 degrees. Okay, that gives you 34.9732 newtons. Okay, again, I'm not showing all the steps. It's a lot to type out. Over here, I'm going to use cosine because this is adjacent to my angle. And I would say that cosine 36 degrees equals adjacent over hypotenuse. It's the ca and SOHCAHTOA. But I'm solving for this, so I do 59.5 times cosine 36 degrees, and I get that, 48.1365 newtons. It's the same process as we did before, I just didn't show all the work on the screen. Okay, so again, this one I had to use sine, this one I had to use cosine. So if you have a force that is in a diagonal direction, break it into components, always first step. Okay, I know that there is friction acting on this. I don't know what it is, I only know the coefficient. Okay, I can solve for force of friction using the equation force of friction equals mu times normal force, or coefficient of friction times normal force. The problem is I don't have the rest of the forces here, so I don't know my normal force yet. Okay, so I'm just labeling the arrow for now. Okay, I also need to include force of gravity on my diagram because everything has a weight. We're on Earth, we have gravity, Earth's gravitational field pulling down on this box, giving it weight, Fg, downward. And then of course Fn is upward. And I know it's going to be shorter than Fg because I know that Fn will add with this vertical piece to equal Fg. You don't have to necessarily draw it to scale until you've got the numbers, but you know, it's at least somewhat to scale right now. All right, so those are the different forces that you would need to draw on this thing, okay? Again, I just moved this one over here so that it looks where it needs to be. So these two together would equal this. My forces up need to equal my forces down because this box is being dragged across the ground. It's not being lifted, okay? It doesn't have any vertical motion, so I need balanced forces in the vertical direction, okay? So I have a different free body diagram over here. I can solve for Fg, okay, and that's our next step because we don't have an equation for Fn. We're going to solve for Fg, mass times gravitational acceleration, and then we know that this value is going to be equal to these two added together. And I know this one's about 35. Okay, I rounded it again just because it looks a lot cleaner than trying to put all those decimals on there. All right, so let's give me some space to work. So the weight or force of gravity, and again, you can use Fg or you can use a W if you prefer, is the mass, which is 12 times 9.8, which gives me a weight of 117.6 newtons. So that is the force of gravity acting on the object, and technically it's downward or negative 17.6 newtons. And again, the downward force has to equal the upward forces. I have two upward forces, Fn and this one that is the vertical component of that diagonal force. It's about 35, but I have 34.973 here. If I want to solve for Fn, I obviously need to subtract that from both sides, and Fn will be equal to 82.627 newtons. Let me pause here for a second. Does anybody have a question about any of the pieces I've done so far? You have to be able to get to this point on your own. Okay. So the reason we need this is because we don't have friction given to us like the last one. They gave us the coefficient. Okay, if they give us a coefficient of friction, we have to get the normal force so we can find force of friction. The equation shows you that. Okay, so in order for us to find force of friction, we had to get this number. Okay, and so that's our next step. Force of friction is the coefficient of friction, which is 0.27, that's in the question, times normal force, which is the number we just found, 82.627. When I multiply those two values together, I will get my force of friction, and technically this is negative. You can see it in the diagram, it goes off to the left. Okay, so if I was actually reporting it as an answer, I would want to put negative 22.31, but of course when you use this force of friction equation, it's only going to give you the magnitude. You're not going to get a negative number anytime that you use that equation. So now I know my force of friction is 22.31 newtons. Over here it is to the left, so it would be better if I labeled it as a negative. Okay, but if you label it on the diagram, you can see that it's negative, so you don't have to put the sign. All right, so I put all the numbers on here, so now we have everything labeled in the picture, and we're trying to find the acceleration. Again, vertically, my net force is 0. So my acceleration is going to be the result of a net force in the horizontal direction. I only have two horizontal forces. I have 48 newtons to the right, and I have 22.31 newtons to the left. Okay, and so in order for me to find acceleration, I need to get my net force. Again, vertically, I don't have any net force, so I have no vertical acceleration. Horizontally, sum of my forces, 48.1365 plus negative 22.31. I've added more decimals here, so you can actually see the more accurate numbers, or sorry, more precise numbers from the calculator. So 48.1365 plus negative, or just minus 22.3092, gives me a net force in the x direction of 25.83 newtons to the right. You have to find that so that you can find acceleration. Your acceleration isn't due to the whole 48 newtons now, because now friction is going to cause it to accelerate less. Okay, it's going to slow it down. You're not going to have the same rate of acceleration due to the friction. Okay, so 25.83 is what's going to cause the acceleration. So don't just use this if there's friction. You can't do that. All right, so now that we have a net force, we can find acceleration using F net equals m times a. So this is my total net force, 25.83 newtons to the right. Okay, and then we're going to plug it in here. So F net, 25.83 equals the mass, 12 times a. Again, I'm trying to isolate my variable a, so I'm going to divide both sides by 12. 25.83 divided by 12 equals 2.15 meters per second squared to the right. That is as lengthy as these problems get. It's a lot of steps, but if you start by drawing the diagram, okay, and you start calculating the pieces as you go, you're going to get there, okay, as long as you know how to find weight, as long as you know how to use the weight to, you know, or get your components, all that stuff. Okay, you should be able to get to this point. But does anybody have a question about this particular problem? by the way, if you do choose to come back and look at this later on, I'm currently on slide 43, which is the end of the problem, so it started a couple slides before that, but you can go back and look at any part of today's notes. All right, here's just kind of a follow-up question. It says, if the free body diagram represents a kid pulling a box of toys, which it did, okay, how does the normal force compare when the box is not being pulled? If he drops the rope and stops pulling it, what's going to happen to the normal force? Is it going to stay the same? No. Because right now he's lifting it a little. I mean, he's not actually lifting it off the ground, but he's applying some amount of force upward. If he stops doing that, your normal force is going to be greater because, again, your vertical forces are going to need to stay balanced. So if he stops applying his vertical force, okay, then the floor is currently lifting part of it, but the floor is going to have to lift more of it. Again, upward forces on an object that sit or move along a surface result in a smaller normal force from the surface. The ground isn't doing all of the lifting part for you. Okay, so if you pull something at an upward angle, your normal force is going to be smaller than your force of gravity. And if you let go of that rope, now they're going to be equal to each other again, just like they were in the last unit. All right, guys, that is it for the notes today. That should be enough to help you get through the types of problems that are in this assignment. You should have started it yesterday, but you can finish that today. 401.2, two-dimensional second law problem set is due tonight by 11:59 p.m. You'll notice when you go through it, and you should have noticed this yesterday, not all the questions even have two dimensions. Some of them should look really familiar because you did them in the last unit. Okay, some of them are just along the flat surface. You still need to know how to do those types of problems as well. We're just adding angles to it. But if I did them all at an angle, that would take you a while because, as you notice, those problems, they take a while. So only a few of them are at an angle, and some of them, and the rest are horizontal or just pieces of a problem or multiple choice. Go ahead and get to work on it. You guys have 25 minutes, so you've got a lot of time to be able to practice, and if you get stuck, to be able to ask questions. Use that time wisely. Okay, don't wait and do it later and then get home and say, I have no idea what I'm doing. Use your time right now to try some of these. That way, if you do figure out, I thought I knew what I was doing, but I don't, you can ask for help. Okay, so again, I'm going to let you guys get to it. If you have questions for me, please let me know.